Please like, share and subscribe our channel to learn and enjoy our free online educational videos from class nursery to 10. Please click the bell icon to get all new updated videos.
Lesson 4. Structure of the atom. Atoms and molecules are the fundamental building blocks of matter. The existence of different kinds of matter is due to different atoms constituting them. Subatomic particles and the various models that have been proposed to explain how these particles are arranged within the atom. Atoms are not indivisible comes from studying static electricity and the condition under which electricity is conducted by different substances. Charged particles in matter. Comb dry hair. The comb then attracts small pieces of paper. Rub a glass rod with a silk cloth and bring the rod near an inflated balloon. The rod attracts inflated balloon. It shows that on rubbing two objects together, they become electrically charged. One subatomic particle, the electron, identified by J. Thompson. Even before the electron was identified, E. Goldstein in 1886 discovered the presence of new radiations in a gas discharge and called them canal rays. These rays were positively charged radiations which ultimately led to the discovery of another subatomic particle. This subatomic particle had a charge equal in magnitude but opposite in sign to that of the electron. Its mass was approximately 2000 times as that of the electron. It was given the name of proton. In general, an electron is represented as E negative and a proton as P positive. The mass of a proton is taken as 1 unit and its charge as +1. The mass of an electron is considered to be negligible and its charge is -1. It seemed highly likely that an atom was composed of protons and electrons mutually balancing their charges. It also appeared that the protons were in the interior of the atom. The structure of an atom. According to Dalton's atomic theory, in which suggested that the atom was indivisible and indestructible, but the discovery of two fundamental particles, electrons and protons, inside the atom. J. Thompson was the first one to propose a model for the structure of an atom. Thomson's model of an atom. Thompson proposed that 1. An atom consists of a positively charged sphere and the electrons are embedded in it. 2. The negative and positive charges are equal in magnitude, so the atom as a whole is electrically neutral. Although Thomson's model explained that atoms are electrically neutral. Rutherford's model of an atom. Rutherford designed an experiment for this. In this experiment, fast-moving alpha particles were made to fall on a thin gold foil. He selected a gold foil because he wanted as thin a layer as possible. This gold foil was about 1000 atoms thick. Alpha particles are doubly charged helium ions. Since they have a mass of 4u, the fast-moving alpha particles have a considerable amount of energy. It was expected that alpha particles would be deflected by the subatomic particles in the gold atoms. Since the alpha particles were much heavier than the protons, he did not expect to see large deflections. But the alpha particle scattering experiment gave totally unexpected results. These observations were made. 1. Most of the fast-moving alpha particles passed straight through the gold foil. 2. Some of the alpha particles were deflected by the foil by small angles. 3. Surprisingly, 1 out of every 12,000 particles appeared to rebound. Rutherford concluded from the alpha particle scattering experiment that 1. Most of the space inside the atom is empty because most of the alpha particles pass through the gold foil without getting deflected. 2. Very few particles were deflected from their path, indicating that the positive charge of the atom occupies very little space. 3. A very small fraction of alpha particles were deflected by 180 degrees, indicating that all the positive charge and mass of the gold atom were concentrated in a very small volume within the atom. On the basis of his experiment, Rutherford put forward the nuclear model of an atom, which had the following features. 1. There is a positively charged center in an atom called the nucleus. Nearly all the mass of an atom resides in the nucleus. 2. The electrons revolve around the nucleus in circular paths. 3. The size of the nucleus is very small as compared to the size of the atom. Drawbacks of Rutherford's model of the atom. The revolution of the electron in a circular orbit is not expected to be stable. Any particle in a circular orbit would undergo acceleration. During acceleration, charged particles would radiate energy. Thus, the revolving electron would lose energy and finally fall into the nucleus. If this were so, the atom should be highly unstable, and hence matter would not exist in the form that we know. We know that atoms are quite stable. Bohr's model of atom. In order to overcome the objections raised against Rutherford's model of the atom, Niels Bohr put forward these postulates about the model of an atom. 1. Only certain special orbits, known as discrete orbits of electrons, are allowed inside the atom. 2. While revolving in discrete orbits, the electrons do not radiate energy. These orbits or shells are called energy levels. These orbits or shells are represented by the letters K, L, M, N or the numbers n equal to 1, 2, 3, 4. Neutrons. In 1932, J. Chadwick discovered another subatomic particle which had no charge and a mass nearly equal to that of a proton. It was eventually named as neutron. Neutrons are present in the nucleus of all atoms except hydrogen. In general, a neutron is represented as N. The mass of an atom is therefore given by the sum of the masses of protons and neutrons present in the nucleus. How are electrons distributed in different orbits, shells? The distribution of electrons into different orbits of an atom was suggested by Bohr and Berry. These rules are followed for writing the number of electrons in different energy levels or shells. 1. The maximum number of electrons present in a shell is given by the formula 2n2, where n is the orbit number or energy level index 1, 2, 3. Hence, the maximum number of electrons in different shells are as these. First orbit or K shell will be 2 multiplied by 1 square equal to 2. Second orbit or L shell will be 2 multiplied by 2 square equal to 8. Third orbit or M shell will be 2 multiplied by 3 square equal to 18. Fourth orbit or N shell will be 2 multiplied by 4 square equal to 32, and so on. 2. The maximum number of electrons that can be accommodated in the outermost orbit is 8. 3. Electrons are not accommodated in a given shell unless the inner shells are filled. That is, the shells are filled in a stepwise manner. Valency. The electrons in an atom are arranged in different shells or orbits. The electrons present in the outermost shell of an atom are known as the valence electrons. From the Bohr-Berry scheme, we also know that the outermost shell of an atom can accommodate a maximum of 8 electrons. It was observed that the atoms of elements having a completely filled outermost shell show little chemical activity. In other words, their combining capacity or valency is 0. Atomic number and mass number. Atomic number. We know that protons are present in the nucleus of an atom. It is the number of protons of an atom which determines its atomic number. It is denoted by Z. All atoms of an element have the same atomic number Z. In fact, elements are defined by the number of protons they possess. For hydrogen, Z equal to 1. Because in hydrogen atom, only one proton is present in the nucleus. Similarly, for carbon, Z equal to 6. Therefore, the atomic number is defined as the total number of protons present in the nucleus of an atom. Mass number. Mass of an atom is practically due to protons and neutrons alone. These are present in the nucleus of an atom. Hence, protons and neutrons are also called nucleons. Therefore, the mass of an atom resides in its nucleus. For example, mass of carbon is 12U because it has 6 protons and 6 neutrons. In the notation for an atom, the atomic number, mass number, and symbol of the element are to be written as mass number, symbol of the element, atomic number. For example, nitrogen is written as 147N. Isotopes. In nature, a number of atoms of some elements have been identified which have the same atomic number but different mass numbers. For example, take the case of hydrogen atom. It has 3 atomic species. namely protium, deuterium, and tritium. The atomic number of each one is 1, but the mass number is 1, 2, and 3 respectively. On the basis of example, isotopes are defined as the atoms of the same element having the same atomic number but different mass numbers. Therefore, we can say that there are 3 isotopes of hydrogen atom, namely protium, deuterium, and tritium. Applications. Since the chemical properties of all the isotopes of an element are the same, normally we are not concerned about taking a mixture. But some isotopes have special properties which find them useful in various fields. Some of them are: 1. An isotope of uranium is used as a fuel in nuclear reactors. 2. An isotope of cobalt is used in the treatment of cancer. 3. An isotope of iodine is used in the treatment of goiter. Isobars. Atoms of different elements with different atomic numbers which have the same mass number are known as isobars. Calcium, atomic number 20, and argon, atomic number 18. The number of electrons in these atoms is different, but the mass number of both these elements is 40.